Hi, today we will continue our discussion and we have the topic design philosophies. We actually have three design philosophies in structural engineering: the working stress design, WSD, or allowable stress design, ESD. Also, we have the strength design method, SDM. This is used in reinforced concrete design, the load and resistance factor design, or LRFD, in the design of structural steel. And aside from that, we can also use the plastic design. I will just give you short introductions of this design philosophy so that you will be able to understand how the entire process of the entire design process are done. But before that, we need to review the structural loads. For the dead load, we have the reinforced concrete around 23.56 kilonewton per meter cube, and the structural steel is around 77 kilonewton per meter cube. If you want to know other unit weights, you can refer to ESC 7-16 or the NSCP 2015. Also, we have the live load. For residential, that's 1.9 kilopascal, office 2.4 kilopascal, in light storage 6 kilopascal. The rest of the live loads can also be referred to our references. Also, we have the wind load. Minimum of 0.766 kilopascal should be used. And for Bukidnon, wind velocity is around 250 kilometer per hour. And we also have the earthquake load. Normally, uh, in terms of the base shear, which is equal to the seismic coefficient times the weight of the building. Again, for all the structural loads, the specifics and other loads that I did not include, you can refer to ASC 7-16 or the NSCP 2015. For the first design philosophy, the working stress design or allowable stress design, from the word itself, we have to use or we have to design it in terms of the working stress or the allowable stress. Our load should not go beyond the allowable stress. So normally, there should be combination of loads. A dead load plus a fluid that is F, or pwede din matanggal ang F because there are times that only dead load. So you can compute the actual stress in terms of dead load only, or a combination of other loads: dead load plus live load, dead load plus roof live load, or snow or roof, whichever is higher. Also, we have dead load plus 75% of the live load plus 75% of the roof live load, or dead load plus zero point 0.6 of wind or zero point 0.7 of earthquake. So you can continue to the bottom. Also, for the strength design method, we are not using working stress here, but we are using the ultimate strength of the material. So here, since we are using the ultimate strength, normally we have to multiply the loads by a certain factor. Uh, so for dead load, we normally multiply it by 1.4. Uh, for live load, a combination of live load and dead load, the load factor is 1.2 for dead load plus 1.6 for the live load plus zero point 0.5 for the roof live load. But if there will be combination of wind, uh, the third equation you can use, and the fourth equation. And if you have a combination of earthquake, dead load, live load, and earthquake, you can use 1.2 dead load plus 1.0 earthquake plus F1 times the live load. And the rest of the equations you can use. Okay, so this is how we do it. For the reinforced concrete design, in the working stress design, the equation involved is that the actual stress should always be less than or equal to the allowable stress. Normally, the allowable stress for the fiber stress and compression, it should be 45% of FC prime, where FC prime is the design strength at 28 days. So, uh, 45% only you can use. For the reinforcement, grade 70, 276 reinforcement, the allowable stress is 50% of the tensile strength. That's 140 megapascal. And also for grade 420 reinforcement, the allowable stress is only 40% of Fy. That's 170 megapascal. For the strength design method on the reinforced concrete design, the basic equation is that the required strength should always be greater than or equal to the ultimate strength. The ultimate strength can be taken from the structural analysis, the combination of loads, the 1.4 dead load or 1.2 dead load plus 1.6 live load or 1.2 dead load plus zero point 0.5 live load plus 1 earthquake. We have to analyze the structure using the different loads and then multiply it with the load factor and then add everything to get the ultimate strength. In terms of bending moment, that's mu. Also, pi as the strength reduction factor. Normally, the strength reduction factor is 0.9 for flexure, 0.75 for shear and torsion, and zero point 0.6 to zero point 0.9 for columns. Mn is the nominal strength or the nominal moment in this case, which is normally taken from the internal force T times the distance between T and C, or C times the distance between T and C. The internal force that I discussed to you earlier. And the tension T, if it is reinforced concrete, should be equal to the area of the rebar times the tensile strength Fy. And for the compressive strength, you can compute for the compressive strength in terms of the dimension of the beam. So here, if you have the ultimate moment and then you have the strength reduction factor, also you have Fy and the dimension of the beam, you will be able to determine the number of rebars. So that's how we do the design, the proportioning to determine the size of the section and the number of rebars. Aside from that strength design, we normally design in terms of deflection limits. We cannot go beyond intolerable deflection because siyempre malipong po mo, mahadlok mo. So normally there is a deflection limits. Like for example, for the floor beams, for the live load, it should be the length of the beam over 360, or dead load plus live load, that's L over 240, depending on your design. So aside from the design philosophies, we can now continue our discussion on the behavior of the portal frame. What is portal frame? Just like this one, a portal frame nasa column, dua, tapos na beam connected. So here again, I presented to you two types of supports. The first portal frame, if it is hand support and roller support, and the second one is fixed support. So as you can see, the deformations, reactions, and the moments. Here, the moments, medyo dako ang moments sa gravity load for the portal frame sa midspan. Dili siya parehas diri sa ubos. But at the bottom, the columns has bending moments also. Sa taas, wala. But if you have to apply a lateral load, what will happen? Kining first portal frame, dagko iyang moments 80 sa beam o sa column. Pero sa fixed ended nga mga support 16 lang, gamay-gamay ra siya. 24 ang pinakadako sa ubos. But take note, sa taas walay bending sa support, pero diri sa ubos na siya bending. So when you design, you have to check that one. So if we have to combine that one, as I mentioned in the strength design method, we use the load factors, 1.4 dead load, 1.2 dead load plus 1.6 live load, and the rest of the load combinations. If we combine everything, these are the result. So as you can see, the ultimate moment from the first frame, the moment is 80. Here, the moment is negative 95.8. So we will be using the maximum moment. Siyempre, kinipix ended. minus 95.8. Katong sa taas roller minus that's 80. So mas gamay ni siya. So actually much better ang ibabaw nga portal frame, but depende ra gyapon sa inyo because you are the designer, you can choose between the two, but the important thing now is that you should know the characteristic and the possible quantity. And so with the axial load, the maximum is minus 36.6. For the ultimate share, the maximum is 127.8. They are the same actually sa mga beams. O yung kalainan lang, yung moment o yung axial force. So we will be using this data maximum to design the beam. If we design the beam, kining sa taas, 127.8 kilonewton ang ang share. Ang yung moment is 95.8. You can use a software, we call it GEAR. I also included it in our Google Drive, the GEAR, General Engineering and Reference, I think. So here, you will have the material properties and then the moment and the share. And if you have to design it, click the design option. It will give you the number of reinforcement, 616. And then since I choose the area or the section 300 by 450, so it gives me a number of rebars 616. Yan na lang, yan na siya kasayon. Pero syempre, when you are designing manually, it will really take time. Task with siya. But if you use software, it gives you a very fast result. Aside from that, the effect is that this one, as you can see, going back, here we have a negative moment, positive, negative. So, na diri sa taas ang tension, diri sa ubos ang tension, taas tension. Kini bali man ni siya negative, so na diri ang tension ana. But that's a combined, but for the gravity load mo ni siya. So that's the result here I presented, and as you can see there is the cracks. Tungod kay tension man siya sa tunga sa ubos, so diri mag-start ang cracks. Ang sa taas, tension sa taas, so diri po mag-start ang cracks. So diri na to pang butangan og buthaw. These are the rebars for the gravity effect. But it's not only the gravity load. Okay? So napud siya lateral load that can be earthquake or wind. So what will happen kung na lateral load? So sa earthquake, simply the earthquake goes back and forth. So this is the seismic action. The result would be here. This is the cracks. But this can be verified if you have to go back to the behavior by lateral load. So as you can see, kung fixed-ended siya, positive yung mong moment, diri negative. So mapali siya ang tension na sa ubos, compression sa taas, diri tension sa taas, compression sa ubos. So you will see the effect. Ayan. So mo diri man ang tension, so diri na pud imong buthaw. If the force is coming from here, kaya nabali man siya tension, baliday kung gikan diri ang kuan kay seismic effect is from right. Then kung bali na pud siya diri gikan, so diri na pud ka magbutang buthaw. So because the earthquake is motion is back and forth, so almost the reinforcement for a portal frame is complete. So this is the complete reinforcement for that one. Okay, and then we have the two-story, two-bay frame. So I just want you to see how it was done. This is again a two-story, two-bay frame with different supports, a hinge support or a fixed-ended supports. You can see the effect of the superimposed dead loads. This is the usual bending and the bending due to the live load and the bending due to the earthquake, and then you can combine these loads to give you the maximum effect. Normally we use the design envelope, meaning you have to draw all the share and the moment diagram due to different loads, and you will see the maximum. So the maximum is or the design envelope uh, boundary siya sa minimum maximum values. So you will see here the design envelope for this structure. The maximum MU is minus 110. The share is 130. So again, you can design the beam using gear. You just put the material strength and the values for MU and VU, and it will give you the number of reinforcement. Here I just choose the section 300 by 500, and it gave me 420 millimeter rebar. Also, the reaction due to the service load, self-load, dead load, and the live load, you can use that one for the design of puting, the area to be occupied by the puting. A simplified computation is that you will get the reaction, vertical reaction 266, and you have to divide it with the allowable soil pressure, assuming 200, and then take the square root. So the length is 1.15 meter, or approximately 1.2 by 1.2 by 0.3 meter, with 712 mm both ways. I just computed it myself using design concept from beam. So here, this is around zero point 0.8 by zero point 0.8 by zero point 0.2. And to determine the reinforcement for the footing, as you will notice, we have to apply the force from the column. Siyempre, you have to remember the load paths gikan sa slab to the beam, to the girder, to the column, and to the foundation. So this is the force coming from the column, and there will be a reaction from the soil or the foundation. And if you imagine this one, this is baliktad nga beam, nasa ubos ang mga loads niya na dire ang reaction sa taas. So what will happen, the behavior of this footing is that ingunani siya, it will be concave upward. So what will happen, sa ubos ang tension. So that is why all of our reinforcement are located at the bottom for the footing. Okay, this is only for the isolated footing. Also, for more rebar detailing, the continuous beam has almost the same effect with the continuous one-way slab. So, butaran niya po niyo puthaw accordingly. So, tension man siya diri, tension sa ubo. So, manang ingani ang location sa mga puthaw. Or you can see the elastic curve with the corresponding cracks. So, kung asa mag-crack, nga dagko ang concrete dito na yung butangan o rebar. So this is the 3D illustration of a continuous one-way slab, including the cantilever. Also, for a beam with high ductility requirement, this is how we do this one. Do it. This is the cross section. This is the 3D. Lastly, we have the column. We have the number of reinforcement here, the vertical reinforcements, and the ties. This is designed for seismic effects. Okay, that's all for now, and I hope you're able to learn a lot of things in the behavior of the structures, and now you are ready to tackle structural analysis, and later on you can do structural design. Thank you for listening.